up, you beautiful coders? We're here with another episode of Conquering the JavaScript Interview. Hand motions. Today we're delving into the exciting world of prime numbers. Yeah, I know. Eye rolls. Math might not be everyone's cup of tea, says guy that just made another video about a math-oriented algorithm. But this one is a simple one we can tackle very quickly. It is a very, very universally asked algorithm-style question. Determining if a number input is prime or not, right? Sounds simple enough on its surface, but we can ratchet up its optimization with one cool trick. So we're going to learn how to break down the process of checking a number is prime, step by step, and I'll show you some cool tricks to simplify the math. So put on your thinking caps and let's dive into the world of prime numbers, and also tell you why they're kind of cool in coding, because I learned this while researching for this video. So as a quick refresher, first off, the purpose of this algorithm is to write a function that takes a number argument n and returns true or false if that number is a prime number or not. So as a refresher for people that have been out of Scholastic program for forever or just forgot what primes are, a prime number is a number that can only be divided by itself and 1 without any remainders, right? So that will include numbers like 2, 3, 5, 7, 11, 13, 17, 19. I had them written off screen. It's not like I'm that good. I haven't got all these memorized. But yeah, those are examples of prime numbers. For example, the number 4 is not a prime number because it's divisible by itself, divisible by 1. Oh, that sounds prime, but you can also divide it by 2 with no remainder, which means it now has 3 factors. You'll hear me say that word a couple times throughout this video, so as a brush up on our skills on that one, when I'm talking about factors, I'm talking about the divisors of that number, right? So, for example, in my examples right here, I have 51 written down, right? And 51 has itself, 51, 1, 3, and 17 as divisors. That means it has 4 factors, right? So that's how many times it can be evenly divided to get that number, right? So that is what I mean with the term factors, and hopefully now everyone is like, oh yeah, that's what prime numbers were, now that I've kind of refreshed everybody here. All negative numbers and 0 are not considered prime, and 1 is also not considered a prime number, because prime numbers have to have exactly 2 factors, whereas 1 doesn't have it. It only has 1 factor itself, so 1 is not considered a prime number. Hint, hint, that sounds like some maybe alarm bells going off for like adding some early exit conditions to our algorithm here. And 2 is a prime number because it has 2 factors, namely 1 and itself 2. And there you go. So with that in mind, it sounds fairly simple to implement, and then I'll show you a cool trick to make it way more efficient, optimized, and make you look super cool to your interviewer should you get asked this kind of question. All right. On its surface, it seems like all we have to do to determine if a number is prime in a programmatic or coding perspective is we're going to loop through all the numbers up till our number and see if any one of those numbers up to our number gives us, when divided by, gives us no remainder. Because if we get a modulus operation with no remainder, that means, hey, it has another factor, which means it can't be prime, and we can stop there and return false. So, saying that out loud hopefully made it kind of clear as to what the logic is going to be. Again, like, this is this is as simple as, and we know 1's not a prime number, so I'm actually going to start my loop at 2 instead of 1. And then you can also say, well, Luke, we already know 2 is a prime number. Why run any iterations at 2 when we can just return 2 early? And again, we can talk about those early conditions and things like that. But I'm going to choose to start this loop at our first prime number, which is 2, and move onwards from there. But like I was saying, on the surface, it's very simple, but we can ratchet it up a little bit further from this. So it's like, oh, okay, Luke, so I'll just make a loop that goes through all the numbers up to, but not including ours, because that'll be a factor anyway. If any one of those numbers that we're iterating through, when divided by our number, not 2, what am I doing? If any one of those numbers that we're looping through evenly divides into our input number, then it can't be prime. It has more than 2 factors. How dare you? So we can say return false and just stop the function in its tracks right there. The loop will stop. All is fine. And therefore we can say if the loop completes its entire iteration and it never actually gets to a return false. That means this number is probably prime, and we can return true. And on its surface, that's what I expect any very beginner student to be able to answer. So if this is what you want to take a screenshot of and memorize, that's fine. But we're going to ratchet it up a bit further from here. So let's first off go ahead and run some of my tests up here. 517, 1851. So let's go ahead and console log 5. Hopefully we do indeed get true, as a 5 is a prime number. That's what I'm talking about. We also had 17. 17 is also a prime number, so I'm talking about. 51 had 4 factors we had learned, so definitely not a prime number. And 18, we know it can be divided by 3, 6, 9, 2, it's definitely not a prime number. It's got too many factors for us, bro, all right? Too many factors. We only want 2 around here. So that is what our prime logic looks like, and guess what? That is good enough to technically pass the test and solve it. But if you want to talk about optimizing efficiency and learning this one simple trick that mathematicians hate, there's actually a bunch of cool ways to pick out prime numbers, and there's actually a whole I'm not even okay. I'll show you the one cool trick and not all the cool tricks, because again, my math background was heavy in university, but a decade after university, don't remember as much because I don't use it most of my life. But here, there is a cool thing we could do with square roots that will really ratchet up what we're looking at here. Okay, there's a bit of magic that we can do. So when we're iterating through a loop to find prime numbers, we do not have to actually loop all the way up to our number. We can instead loop up to and including the square root of our number. So this one little trick massively can cut down the number of iterations our loop would do, making this a much, much more optimized solution compared to looping through every single number. Again, with this math trick, we know that there's a definitive stopping point where the number can no longer be prime. If it's greater than its own square root. And I'll try and break down that logic for you guys here in a second. And again, I'm not trying to make this into a math lesson. I'm just trying to show y'all a really cool way to optimize this, and you'll see it across posts on the internet as well. So what is happening here? So how do I describe this? Let me break down why it works. Okay, so say we have a number n, right? If n is not a prime number, it can be factored into at least 2 numbers, a and b. So what we're looking at here is the following. Say we have a number, which we do. We know that it can be factored into 2 numbers such that their product, their multiplication, gets us that number, right? And that's what our factors are for our prime numbers, right? We know that we can multiply 2 numbers to get another number. Now, we know that at least one of these factors, a or b, it has to be less than or equal to the square root of n. That's because if both factors were greater than the square root of n, their product would be bigger than n, and that's not true, right? We are not looking at this equation and saying, a times b is greater than their product is greater than n. That's not possible, because we know the two numbers multiplied together must be n, not greater than n. And so what we're looking at here is basically some logic in between here in this mess that I'm looking at. Is a cannot be greater than the square root of n, and b cannot be greater than the square root of n. And that, because if they were, it would mean that a and times b would be greater than n, and that's just not mathematically possible. So while this is not, again, for non-math heads, this is probably a terrible explanation. Get in the comments below if you have a better one, or a link to a video that could illuminate this with a better diagram than some comments in a text code editor. Again, I don't want to delve in heavy into the math. I just want to show you all the cool trick. But yeah, basically there's some logic that says, hey, we can only loop up into n including the square root of n rather than all the way up to n to super optimize this particular solution. We can also have an early exit condition to consider as well. We can say if the number is less than or equal to 1, we can return early because we don't have to run anything. We could also add in the exception of if it is 2, we can say if n is equal to 2, we can just return true because we already know that input number is a prime value. And from there, you know, we technically also wouldn't have to keep looping through. Now, I'll leave it at this. So yeah, this one little trick is how you make this efficiency so much better, and it what gives us a cool big O complexity of square root n. And I realize in my videos I've never actually shown y'all square root complexity. And by the way, this should also, if I save this, hopefully give us false. There we go. So it still works. 51 should also still be false. Awesome. Another prime number. Let's do 53 as a prime number. True. Okay, cool. So it still works after my little optimizations there. But again, it goes from a worse complexity into a better one with the cool trick I showed y'all into a square root of n. So I'm going to see if I have that picture, if I got it ready for us here. Where are you, PNG? Hey. So yeah, this is what we're looking at in terms of big O notation and what I've been talking about of how complex these get. We are looking at a square root of n, meaning the bigger the input gets, we don't trade off a whole lot of operations. So it makes it way better than what we were doing before, which is a linear n right here. So the bigger our input got, the worse our number of operations had to go. So we drastically cut down our number of operations from a big O of n to square root n instead. And I think that is pretty cool to note and to learn. Right on. And if you're wondering why primes or isPrime seems to be such a common algorithm that you'll see in like coding books and interview prep and my video series as well, that's because that prime numbers are super crucial in cryptography, right? So cryptographic algorithms, which ensure the security of communication and data transmission between you and me and our computers, is all based on prime numbers. The RSA encryption algorithm, widely used for secure communication over the internet, 2 large prime numbers are used to generate a public key and a private key. The security of that algorithm is based on the fact that it's extremely difficult to factorize a large composite number into its prime factors, especially if the prime factors are very large. So prime numbers are also important in hashing algorithms, which are used to map data of arbitrary size to fixed size values, right? So we've talked about hash tables in past videos here. And again, prime numbers can be very, very useful there to ensure that hash values generated are reducing collisions so we don't get any kind of mix-ups on our hash tables, right? So they're very important in hashing, cryptography, and coding in general. So, you know, having this basic idea of how to find them and how to make the operation far more efficient is the baby's first steps into a world of cryptography and hashing and, you know, error correcting codes and all that other kind of crazy stuff that I was Googling. But yeah, that'll about round it up for this video. Thanks for watching it. I hope we are all enjoying this journey together because I'm learning just as much from y'all to become a better developer. If you enjoyed the video, consider giving us a thumbs up, like, comment, subscribe, all that YouTube stuff. You know, get us going on the algorithm here. Also, I would love to hear your thoughts on the algorithm that we covered in this video, and if you can make it better. There are some cool things you could do. If there's some math heads that are watching this, show me some of the cool stuff you could optimize the for loop with even further. Remember, constructive and positive comments are always welcome here. Let's keep the vibe going and helping each other out. Thanks again for tuning in, and I'll see y'all in the next video.